bright students came to pick me up, Rushil and Bruman, if I said their name correctly. And they told me that the audience is going to be very diverse. There are undergrads, masters, PhDs, and then there are professors. So I tried to change the slides a bit so that I cater to everybody a little bit. So I'll start slow and then probably go into more technical details. If I lose you in the later part, don't worry about that. Okay, I just want to give you a high-level story. That's my main goal. So let's get started. I'm going to talk about computer equilibrium with chores. So first of all, what is chores? Chores, by chores I mean bads, something that gives you negative utility. So let's say mopping the floor is a chore, right? A laptop is a good. You want to have a laptop, but probably not mopping the floor. And then I also thought, let me also mention applications of this really important notions from economics to fairness that the Vijay talked about and also Roni like hinted to. So what's the setting? So why talk about chores? Whenever we talk about competitive equilibrium, by that I mean market equilibrium, and whenever we think about markets, we always think about goods, right? Grains, bananas, vegetables, things you go and buy, clothes, house, blah, 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 where you pay money to buy it and you get happiness by buying. But I want to argue that the chores market are as prevalent and as important as goods market, and these are essentially labor markets, right? Blinkit, Taskrabbit, Ola, Uber, the drivers are doing the chores to get money earned, right? And the other motivation comes from fair division, as I hinted in the title. Here, what we want to do is we want to allocate a bunch of items to a bunch of agents. The items might be whatever, in the most general setting, goods, stores, whatever. And the agents will have very, very different preferences over these items, and we want to do these allocations so that everybody is happy, and overall we achieve good welfare in the system. So that's what I mean by fair allocation or connection to fairness. Now, when we talk about fairness, this is a little bit tricky notion. Vijay mentioned one fairness notion, which was core. Roni mentioned another through Shapley value, and so on. And so we have to be a little bit careful about that. But why talk about fairness? We already saw that it's very important. And it has, even when we don't involve money and you want to do allocation, you have to talk about fair allocation. Right? So assigning landing slots to airlines when there are bad weathers. Like yesterday, I faced 1 or 1.5 hour delay because there were no takeoff slots available for the flight. Right? Vaccine distribution, school seats assignment, kidney distribution, assigning or dividing assets and liabilities when you are dissolving some company, or inheritance distribution, assigning budgets to or the duties to different arms of defense, and so on. So it's quite important. But what do we mean by some allocation is fair? So let's take a toy example. Let's say we have these two people, our typical suspects, Alice and Bob. And Alice says that I like both chocolate and vanilla. This is a half moon cookie, half side chocolate, half side vanilla. And Alice likes both equally, while Bob says I hate chocolate, I only like vanilla. Okay? How should we do the allocation? How should we divide this cookie between Alice and Bob so that it's fair? So here are three allocations I am proposing. One where we cut the cookie halfway, horizontally. Upper side goes to Bob, lower side goes to Alice. And here sideways in the diagonal, this side goes to Alice, the upper side goes to Bob. And here I'm the vertical cut. This chocolate side goes to Alice, and the vanilla side goes to Bob. Which one do you think is fair? Third one. Why I3rd. The utility, none. The utility, so they are not getting equal amount of, so here Alice is getting only chocolate and Bob is getting only vanilla. They're happy, right? But so in that sense, Bob is getting everything it likes, basically 100% of whatever it likes. And Alice is anyway indifferent, and she is getting 50% of what she likes. But in any allocation, Alice is only going to get, like if you allocate the cookies so that half of the cookie goes to Alice, Alice is only going to get 50%, right? But in either of the case, can Alice or Bob complain that I didn't get a fair, or I like others' allocation better than my allocation? In either of the allocation. In the first allocation, no, because both are getting the same. In the second allocation, no, because Alice doesn't care and Bob is getting more of vanilla than the chocolate that he likes, right? And in the third allocation, finally, of course, that's the best one. So my point is that in my mind, neither of the players can complain that I like others' allocation better than mine. So in that sense, they are fair. But the last one is also efficient. It's actually Pareto optima, right? So that way we can define some, I just tried to give you a hint about the fairness notions that we care about. The first one is envy-freeness, where the allocation is such that nobody should say that I want somebody else's allocation over my allocation. Okay? So I don't envy anybody else. Okay? Proportionality says that everyone gets at least proportional or average of everything. So every agent in the half-moon cookie example getting 50% of the cookie is kind of a proportional allocation. Okay? And in the efficiency side, so we saw that only, so actually if you see in the previous slide, the first allocation actually satisfies both of the fairness notions. So only fairness is not good enough. You have to talk about efficiency also. And then Pareto optimality is an allocation where there's no other allocation which is where everybody is happier, right? You say that, oh, let's reallocate and we all will be happier. Then of course you will all get together and reallocate, right? If there is no such allocation, then we say that this current allocation is Pareto. And finally, welfare maximizing. So welfare maximizing, typically whenever we talk about welfare maximization, we just think of maximizing total welfare, sum of the welfare of everybody. There is something called Nash welfare that Vijay also hinted to, which is in some sense maximizing the product of everybody's value, and it has good welfare properties, better welfare properties in this context than the pure welfare. Because it tries to balance out the utility value. And surprisingly, it has this problem which seems completely orthogonal to market equilibrium, has a very strong connection to market equilibrium in the sense that market equilibrium captures all of them together. If you find a market equilibrium or competitive equilibrium solution or allocation, it will satisfy all of these properties together. Okay, and in a minute I'll show you how. Yes. It means that every agent I has a value for the entire bundle of items, right? If it gets everything. Final allocation should be such that it is at least 1/n. If there are n agents, there should be at least 1/n of its value for the entire bundle. So at least average value it should get. So not knowing anything, suppose I am one of the person, not knowing anything about other people's preferences, it might be that all of us value everything similarly. Then I cannot hope to get more than 1/n of the fraction of my value. Okay, so before I tell you what competitive equilibrium is, let me define one slide notation. Okay? 3 things. I'm going to talk about a set of agents. There are n agents or players if you wish. Okay? to whom we are going to allocate things. There are some set of items that I'm going to be allocating, right? And all of these items are going to be divisible. Okay, so it's not, it's like bread, milk, duties, teaching duties, right? It's not like iPhone, laptop that you can't break. Okay, so they are divisible. And finally, agents have preferences over these items. And the preferences are typically defined through concave functions in the economics literature. Okay? And why concavity? Concavity captures decreasing marginal return. What do I mean by decreasing marginal return? It's like this. Suppose we go to have an ice cream. You eat one scoop of ice cream, very, very happy. Eat second scoop of ice cream. Your happiness over the first scoop is not as much as you got for the first scoop. You eat third scoop, you'll be like, okay, I'm getting saturated, right? So your happiness for every next scoop is decreasing. Right? So that's called decreasing marginal returns, and that's captured by concavity. Okay, and finally, our goal is to find a competitive equilibrium in this setting. So what do we mean by market equilibrium? So this is kind of, these agents are going to the market where these items are on the sale. And how are they going to buy these items? Depending on what their preference is over these items, what they like, and how much ever money they have to buy stuff. Right? That is a typical setting in a market. There are a bunch of buyers. They have some money or budget to buy stuff. Right? When we go out in the market, we have some budget, and there are a bunch of items on sale. Items are priced at some price. Depending on the price and how much money they have, they will decide what to buy. Right? Once every agent decides what to buy, let's call that their optimal bundle. This is the bundle that they buy that gives them maximum happiness given how much ever money they have. Yes. Good question. No. Because I'm going to assume free disposal for goods. So even if I give you 100 scoop, you are free to throw it in the trash. Thank you. Yeah. Yes. No. For now, yes. In the evolving market, it will influence. And when we talk about equilibrium, we are assuming that we have reached the equilibrium state. So you are right that so now when every buyer buys what they like the best, there will be a demand. If demand is more than supply, the price is going to go up. If demand is less than supply, the price is going to go down. That's what happens in the market typically, right? And we say that, so thank you for that question, that gives rise to demand. And when demand equals supply, at those prices, we say that they are at competitive equilibrium, at market equilibrium. There was a question? Yes. There could have been another solution. Yes. So that's not the only Pareto optimal and fair solution there. But there could have been another solution where Alice gets 2/3 of the cookie while Bob gets only 1/3 of the vanilla. Thank you. Yes. Okay, good. So in general, the market, the demand and the supply, at least like are reflective of the agent's preferences. Finally, when demand meets supply, we call those prices equilibrium prices. Okay? And this is kind of a bread and butter or really fundamental notion within economics, right? From the perspective of fairness, we say that this equilibrium is with equal income when every agent has same buying power. When we equip every agent with the same amount of money, then and the resulting solution or competitive equilibrium, we call it competitive equilibrium with equal income. Why do we care about it? It easily, just immediately gives us envy freeness. Can anyone say why? The resulting allocation. So assume everybody has exactly same amount of money. You set some prices, they buy what they like, and that defines the demand, and demand meets supply. Okay, so we are at competitive equilibrium when everybody has equal buying power. I claim that whatever they buy, the resulting allocation has to be NV free. Correct. And but why I got what I want, you got what I want, but why can't I say I want your thing? I like it better than yours. We have the same buying power. I could afford your bundle. Why did I buy mine? Then I should not complain. Right? Because of the same buying power, it gives us envy freeness for free. Okay? It's in a social choice theory. So it's a part of social choice theory is a kind of a section within game theory. Maybe network, like in practice, I think it's so in the network bandwidth assignment. And yeah, it's quite useful in that sense. The yeah, so you don't want to make anyone have too much delay, right? Yeah, in the network side. Yeah, so in the allocation problems, when you are really allocating things, like even school fees assignment, you can also talk about in vaccine assignments or, I mean, okay, there are big players and small players, and you should not be like absolutely, but you can also talk about weighted and neatness. If you are a big player, of course, you have a bigger stake, but then you still should not hog everything just because you are a big player. So you can talk about weighted and neatness. When we combine envy freeness with the fact that supply equals demand, that means everything has been allocated, you immediately get proportionality. And this is the exact definition of proportionality, which is everybody gets, if Vi of M was all the set of, the entire set of items, Vi was the valuation function of agent I. This is the value of agent I for the entire set of items. 1/nth of it is at least it should get. That's the definition, formal definition of proportionality. And the first welfare theorem, which is from long time ago, tells us that it's not also very difficult to see, but the fact that everybody is buying what they like the best and everything is getting allocated, again, gives you Pareto optima. And finally, when the valuation functions are well behaved, and I'll tell you what I mean by well behaved, you also get that the final allocation is going to be Nash welfare maximizing. That means it will maximize the product of the values of all the agents. Now, why would you care about maximizing product and not the sum? Suppose you maximize sum, okay? And I am a really boastful person who will always report my values in millions. While you are a modest person and you will report all your values in hundreds. Who will get all the items if we maximize the sum? I will get all the items, because I am always reporting very, very high values, right? So welfare, some of the values is not scale invariant, and which is not a good property from the economics perspective, right? So by the product is scale invariant. Even if I report all of my values, multiply all of my values by 1,000, when you maximize the product, it's just a factor that comes out. It's not going to affect the final outcome or the allocation. So that is one of the properties, and there are more properties that Nash welfare satisfies that are desirable. Okay, and it has a long history. Okay, competitive equilibrium has been studied extensively within economics, with many Nobel Prizes in this area. Within computer science, so economics focused on existence in different of equilibrium in different settings, its properties, stability, multiplicity, and so on, dynamics. and so on. Like how do you reach the equilibrium? In what cases can you reach the equilibrium? How the different market forces affect the equilibrium and so on. From the computer science perspective, we focused on computation. Can you compute these equilibria fast? Because in many of these online markets, maybe we want to compute and see how these prices may get settled. And there has been extensive work, and Vijay was a pioneering person in starting. His was kind of the first paper on algorithms, polynomial time algorithms for market equilibrium. This paper is what I'm talking about. So the previous work that happened within economics were mostly still about structural results like convexity of the set of equilibria and so on. Somewhere here we started talking about polynomial time algorithms and so on. For linear valuations, a lot of good algorithms are known, and then there were simplex. I have also done work in this area with Vijay. So as you go more and more complex valuations, the problem becomes hard. There is some a class which is called PP80 and 6P, sits in NP intersect co-NP, and so that's where you go. The point is when all the items are good, that is positively valued by agents, there is extensive work. But when all the items are chores that are negatively valued by all the agents, there is not much work. And that's what I want to talk about. Okay. So now, when we are in a chores market, how should it work? Will you pay for consuming chores? No. So what should happen? You should get paid, right? So money flow reverses, right? So now that I'll represent by negation. By negation, when you consume it, you get paid by that amount. And again, agents have preferences over chores, and now they have earning requirements. Instead of budgets to spend, they have earning requirements, and they are happy to do these chores and get this utility just because of their earning requirement. Again, based on their earning requirement and the payments that we set, they will demand the optimal bundle. Demand equals supply is computative. Exactly same notion. The money flow has just reversed. Okay. And we can again define computative equilibrium with equal income, where everybody has to earn the exact same amount. And you can also talk about the mixed setting, where you have goods and chores both. And you can define, again, everything similarly. Agents may have budget or may have earning requirement, whatever, here in this case. And a computative equilibrium can be defined in the exact same way. CEEI, equal income, is a little bit tricky because now it's not clear whether the equal budget should be positive or a negative. But I'll tell you a little bit about it later. Okay. So what I want to focus on, again, from the computer science perspective, is computation. How do you compute these equilibria? I told you that for goods, there has been extensive work since 2002 on computation of equilibrium, and we more or less understand the landscape, what we can compute and what we cannot compute. For chores, nothing was known. This paper by Hervé Molla, Bogomolia, Sanovarsky, and Yanovskoy started understanding the complexity of this problem, and they focused on one homogeneous valuation function. These are the valuation functions that are amenable to Nash welfare, the product of the valuation and its connection to computative theory. So this is a class of valuation functions which are subset of concave. The property it satisfies is that if you have an allocation and you multiply that allocation by a scalar A, then your value gets multiplied by the same scalar. That's called one homogeneous valuation. Okay? And many of the interesting classes of valuations from the economics perspective sits inside. This is constant elasticity of substitution. If you don't know about it, don't worry about it. Okay? It subsumes the linear, which is the simplest yet most interesting class. The linear is just additive value. for the homogeneous. Chores. Um, so you mean how the concavity is defined? So it's still concave. So don't think of, think of it still as a valuation. So let's take this offline because it will be, because I'm going to focus on linear throughout. And in linear, it's very clear what it means. Okay, but I'll answer your question offline. Okay. Okay. So they said that when valuation functions are homogeneous, they characterize the CEI completely, which is with equal income. And they said the first thing they observed, so recall that with the, okay, so CE set can be non-convex even when the valuation functions are linear when you have chores, and even when you have only chores. This is in sharp contrast to having convex programs in case of goods for linear, and strongly polynomial and polynomial time algorithms in case of goods, right? And they said that we expect computational difficulties because of this non-convexity of the solution. And this was the main thing, that even for the simplest case of linear valuation, right? What do we mean by linear? You have value for laptop, you have value for iPhone. When I give you both of these things, your value just adds up. Okay? Even that simplest class of valuation, the problem looks very, very difficult. For the goods case, this problem has strongly polynomial time algorithm. Okay? For chores, even the solution set is highly non-convex. Okay? That it can have multiple, many disconnected sets. And the question was, can we really compute such equilibria for chores? Can we even do it approximate? And what we show is that we give a new kind of continuous method. We call it exterior point method to find this equilibria. And so we start with a very simple setting of only bads and linear, and then we extend it to one homogeneous and also to mixed manner. And the main point I want to convey is this algorithmic technique, which is this exterior point method. In follow-up works, we also obtain combinatorial algorithm, and finally, a nice non-convex formulation. Why this formulation is important, it will be clear very soon. I want to focus on this exterior point method as I said. If time permits, I will probably talk briefly about this new non-convex formulation. Okay, so let's get into it. Just again recall our setting. N agent, each one has so I'm going to focus only on bads and only on linear valuation, just to simplify our life. So N agents, each has earning requirement of $1. There are M divisible chores in the market. You can think of as mopping the floor, number of hours you work, okay, in whatever job market. And the hours is divisible. So these are divisible items. And agents have valuations over the allocations of these chores. If Xij is the allocation of chore j to agent I, then her value will be Vij times Xij. Vij is per unit of allocation. Now remember, these are chores. The values are going to be negative. Okay? It's very difficult to work with negative numbers, so I'm going to convert into disutility values. And now the disutilities, here we're going to try to maximize the value. Now we'll be talking about minimize the disutility. Okay? Okay. So what is an equilibrium now? So given prices, remember, agents are going to, given prices, they're going to buy or consume a bundle that minimizes their disutility, subject to the fact that they need to earn $1. Okay? So if you are faced with a bunch of payment options for different types of tasks or chores, and you want to decide what to do so that you have minimum unhappiness and you earn $1, right? Which one will you go for? The ones that minimizes your disutility per dollar earned, right? Bank per kind of pain per buck or bank per buck, right? So agent will demand, so this is the optimal bundle, right? Agent will demand a bundle that minimizes its disutility subject to earning one, but the characterization is that it will only demand those items or those chores that minimizes that disutility per dollar earned, right? And in this case, and finally, when everybody does that, your demand should be equal supply. So now, let's call this such kind of allocation as feasible allocation, where the market clears, demand equals supply. Okay? So now I'm trying to go into the computation or understanding the characterization of such equilibria from the mathematical programming perspective. Okay? Okay, so let's call this X being feasible. Now, Bogomolya, this paper said that if you, over this feasible set, if you minimize the product of the disutility and consider the local optima of this program, this is a mathematical program, right? That will give you the computative equilibrium. So again, the product of the values came into the picture, the Nash welfare. Okay? Yeah. But do you see a very trivial solution, immediate solution to this program? Zero. Just pick one agent, don't give that anything to that agent. The disutility of that agent is going to be zero. And then no matter what you give to others, the product is going to be zero. So those are the dummy solutions. You have to avoid them. Okay, that's the tricky part. Okay. So you're minimizing the product subject to the fact that each of the disutility values has to be strictly positive. Under that, you want to find a local optimum. No. That means that everybody should be given something. No. Just something. Xi is a bundle, right? So Xij is going to be the allocation of job J to agent I. It could be zero, but it should get something so that its disutility is non-zero. The bundle should be non-empty for every agent. Otherwise, I can give an empty bundle to one agent and just make the product free. This exactly reflects the classical Heisenberg-Gale convex program that hinted for the good, where you were exactly on the same feasibility set, you were maxed. Okay, so first of all, product is a difficult objective, so I think I jumped a bunch of clicks, but product is same as minimizing the product or maximizing the product is same as if you apply a log here, log to this term, it becomes sum of the logs, right? So just do that transformation. Log is an increasing function, so you're not changing the optimization problem at all, right? And this is exactly reflects the e.g. Heisenberg-Gale program for good from 59. Okay? There, instead of minimizing, you are maximizing. So if you can solve this fast, why can't you solve this fast? Well, there is a huge difference because your log is a concave function. Sum of the concave function is a concave function. Maximizing a convex concave function is a convex program, and it has a global minimum. Global optima is going to be local optima is going to be global optima. You can find them in polynomial time, not easily, but in polynomial time, right? While for batch, this is a non-convex program because you are minimizing a concave function. And on top of that, you have an open constraint. The only saving grace is that you are only after local optima, not the global optima. Okay? So these local optima are residing on this kind of lower envelope somewhere. This is, I'm plotting the disutility values over all possible allocations. This is the maximum possible disutility values. These are the minimum possible disutility values. When you minimize the product or minimize the sum of the logs and you're finding the local optima, they will be sitting somewhere here. Okay? Now, So what's the issue if we are only after local optima of a non-convex program, gradient descent should do the work, right? What's the problem? Yes. Exactly. That's where you run into the problem, right? So if you try to apply gradient descent, that's where probably you will go, and that's the main problem. Okay. So before we go into the algorithm, I need to tell you about the geometry of this local optima. So what do we mean by local optima geometrically? If this point is a local optima, it should happen that when you draw a supporting hyperplane there and look at the like normal of that supporting hyperplane, it should be proportional to the gradient. That's the definition of local optima. Why is it a local optima in this case? Because when you try to improve this objective, you try to move in the negative of the gradient, and that will take you out of the feasible space, right? Because your gradient is proportional to the normal. So if you try to move in any positive direction with the normal, it will take you out of the feasible space. Okay? So that's another characterization of the local optima. You take that point, draw the supporting hyperplane. The normal of the supporting hyperplane should be proportional to the gradient. Okay. So I'm going to skip this. I wanted to give you a small proof of why this local optima actually give you the computative equilibrium condition. Just believe me, there's a one slide proof. It's a very simple proof. If you want, you can go over that. And because I will have to talk about approximation, how do I define a approximate computative equilibrium? That approximate equilibrium is where every agent earns not exactly 1, but 1 plus or minus epsilon. And that will translate to exactly being approximately approximate local optima or approximate KKT point. So the condition that I said that the normal should be proportional to gradient or approximately proportional to the gradient is essentially the KKT condition. Okay. So what's the big deal? Just apply gradient descent because it's just the local optima. Where the tricky thing is to ensure that every distributive value is non-zero in the sense, in the other words, everybody gets something. So if you try to do the naive or the obvious thing where you move in the direction of the negative of the gradient because you are minimizing, what will happen? You are at some point, you move in this direction. The coordinate, which is the minimum DI, will decrease the fastest. And essentially, that coordinate will very quickly go to 0. Okay? No matter what you do to this objective function, you apply log barrier, do log barrier because there's already a log there. Okay? We tried a lot of experiments. I started working on this problem in 2020. Finally, we got the solution in 2022. So we did a lot of experiments from the interior, nothing worked. And the basic problem is this, what I described here. The minimum coordinate will decrease faster than any gradient descent type of method. Okay? So then, what's the main issue? Because this local optima that we are after are unstable. Most of the points will go to the global optima, which are undesirable, the 0 point. Okay? So then we thought that, okay, instead of going from interior, what if we go from exterior from the below? Now, exterior region is a difficult thing to imagine. It's a non-convex region, right? But if we manage to somehow handle it, then from the below, if you approach, you will be again maximizing or trying to maximize or increase the product, which is amenable to gradient descent because now you will be increasing the smallest coordinate faster. That's what you wanted, right? And indeed, the local optima conditions from interior and exterior are the same, which is this geometric condition that at that point, the supporting hyperplane normal should be proportional to the gradient. No matter whether you do it from inside minimization, outside maximization, that condition remains the same. It's it's a non-convex program. And I'll tell you what happens with the dual at the end if I have time. So non-convex program, we can try and write a dual. Again, it will be a non-convex thing. And we don't have zero duality here because it's a non-convex. But we managed to prove some connection. And yeah, but it doesn't immediately help. It also has this zero-ness issue. Okay, so the challenge now, so first of all, you can only work with this utility space to actually define this exterior region. Even if you manage to define it, it's a non-convex region. Then what should be the potential function for the algorithm, and how do you solve fast convergence? So these are the challenges. So let's first talk about potential function. And ideally, whatever we are trying to maximize, so remember, we were trying to minimize this objective from the interior. Now we are talking about this blue region, and from there we will be trying to maximize the same objective. Right? And from the local optima perspective, both things are the same because geometric interpretation that I told you remains the same. Okay? So when you try to maximize this objective from the exterior, no matter how bizarre this exterior region, will it ever take you to the 0 points? No, because if you go to 0 point, your product or this is going to be minus infinity. That can never be maximum. Right? So you immediately, through this method, avoid the 0 point, which was the main thing. So what we do is that you start with some exterior point, and you project onto the boundary of your feasible region from the below. Okay, this is the Pareto-optimal frontier for you. What we can prove is that the objective in this region is such that this projection is going to be coordinate-wise better than where you started. So this will only improve your potential. It cannot decrease your potential. Second, we say that, okay, either this is a solution and you are happy. If this is not a solution, look at the supporting hyperplane at this point. Okay? And maximize this objective now only on the supporting hyperplane. Right? If this was your solution, you will not go anywhere, right? Otherwise, you will go to another point which will still be in the positive orthant and below this feasible region. Why? Because you are on the supporting hyperplane, so supporting hyperplane is never going to intersect the feasible region. It will only intersect at the boundary. And because you are maximizing, this coordinate can never go negative. So it will remain in the positive orthant. Right? So by the geometry of this current situation of the supporting hyperplane and the feasible region, it happens that when you maximize this objective on the supporting hyperplane, you will again be in this exterior region that we care for. Yeah, it's easy to handle. Maximization is just an, convex program. Yeah. Okay, so in this step, we must have strictly improved our objective. Right? So definitely this is a good potential function to work with, but it might be that these improvements are very, very tiny and we never get to anywhere. Okay, so again, you are in another exterior region, you can repeat the two steps. Project, maximize on the supporting hyperplane. Again, project, maximize on the supporting hyperplane. You stop when your normal is proportional to the gradient. Right? So you keep doing this, and that's our final algorithm. Okay, you keep doing this until you find a local optima. Recall that the condition for the local optima was that if AT is the normal to the supporting hyperplane, then it should be proportional to the gradient. And that's all. The question is, why can't it happen that you just go on and on and on and you never stop at step 3? Okay, you never get this condition right? And we show that this will not happen because either you are at an approximate KKT point or your potential improves at least by a little bit. Okay? And why this is true? Intuitively, in the market setting, what is happening is that you are at a feasible point, and we can show that because you are at the boundary of a distributively feasible space, you are actually the corresponding allocation. Everybody is buying their maximum pain per buck item. So in some sense, quote unquote, optimal bundle. but they might be earning not within 1 plus minus epsilon. Maybe some agents are earning much more than 1 plus epsilon, some agents are earning much less than 1 minus epsilon. So you have to balance this out. And when you do this maximization on the supporting hyperplane, because you are maximizing the product, it automatically balances out the value. So products always balance out the values. So if you have A plus B equals 2 or equals 4, let's say, and you are trying to maximize A times B, what will be the value of A and B? 2 and 2. Product is always maximized when you balance things out, right? And so this is it. Basically, that's essentially the heart of the proof. And we have extension to the homogeneous. And so I want to kind of end with so general homogeneous functions, and to mix manner. I wanted to show trickiness in those two things. Finally, the closed form formulation where you don't have any open constraint, that was the tricky part. We have to go to the dual. And there, again, when you just take the dual immediately, so we don't know how to take this dual, so we take the Eisenberg-Gale dual and just mimic it. And we could show that these local optima of this, again, non-convex program, because you're maximizing a negative of a concave function, maximizing a convex function. It's a non-convex program, but again, local optima are competitive equilibria, except when these variables are all 0. You see that you can set beta to 0, you can set C to 0, and it's a feasible solution, and it achieves the maximum, which is the infinity. So those are dummy solutions. Non-zero solutions are the real solution. Again, the same issue, right? But we show that you add this extra constraint, that the sum of the prices are going to be sum of the budgets, and that has to satisfy when supply equals demand. Everything is taken care of. All the zeros are taken care of. It cuts your feasible space in a way that all the zeros goes away. And then you are only after local optima. And using this, we give Franz-Wolf style algorithm and a better running time. But I want to end with some interesting open questions. The first one is, what is the exact complexity of this problem? Can we have a nice real polynomial time exact algorithm, combinatorial, or just optimization method style, continuous method style? What about dynamics in Chores market? Right? In goods market, we have Titoneman, dynamics, convergence in many goods, many nice valuation function classes. Yes, multi-time period problem, right? And finally, there are applications of competitive equilibrium for goods in the fair division for indivisible items like iPhones and laptops and so on. Can we do that in Chores cases? But in my mind, I mean, these two questions are very important from market perspective. Okay, that's all. Thank you. One homogeneous function, all the way to where we have the characterization for the so when you look at the local optima condition from a geometric perspective, which is you draw the supporting hyperplane, look at the normal, should be proportional to the gradient. This condition remains the same whether you are minimizing from interior or maximizing from the exterior. That's why we are fine.
Yes. This is a very naive question. Could we think of Chores as services? And services again have consumers who want those services. There are positive.
Good. So when you chores as services, so the person who are proposing the chores are getting the service, who are paying for it.
Who want that service?
Yeah,
so
yeah,
they're willing to pay. So in that sense, you view this sort of a good.
Yeah.
I want that service.
I'm
willing to pay.
Yeah.
Likewise, there are providers.
Very good, very good.
And in some cases, I could see that in your chores, maybe the consumer could also be the provider, could do it
Both.
themselves. Like
Yeah,
they
yeah,
do both.
both. Yeah, yeah, yeah. So that's a very good question. We should give a deeper thought to that. Um, the one thing we have to be careful about is that when we start talking about services, then we have to start talking about the budgets of the people who want the service. While here we also want to capture the earning requirements of the people who are providing the service. So you have to capture that part. Second thing we want to be careful about is free disposal. Goods are free disposal, stores are not. And that makes everything different. Okay? Yeah. Yeah, I mean, if you go to, how come? Yeah. I mean, they talked about labor and the firms and so on, but not as rigorously as they did for goods somehow. Like you have this fundamental additive model, Fisher model, all about goods, all about goods. Yes. They were never thought, but even in terms of properties, it's not nice. It's not nice. Yes, you have also worked on recently on chores and sure, yeah, you can talk about chores in the matching markets very. Yes, yes, yes. Any other? There was a question. Okay. Yes. Okay. Thank you.